question of measuring capacitance. So suppose I have a capacitor and I wish to measure how big it is. And suppose I'm not sure where to start. So I don't know. I kind of have an equation for capacitance. I know there's a relationship between current and voltage. Current through a capacitor is C dV dt. So I'm trying to measure the capacitance using some equipment we have in lab. So I'm not sure where to start. So here's how I start. I say, all right, I have no idea how to do that problem. Let me think back to how I would measure the resistance of something. So someone hands me a resistor. Let me think how I would measure its resistance. And suppose I can't use an ohm meter. Suppose I don't have a meter that just, I touch it and tells me the resistance value. If you didn't have an ohm meter, how would you go about measuring the resistance of a resistor? What would you do, Fred?
Current.
Okay, right now I mean connect nothing to it and measure the current, or
Sorry.
so give me the whole thing.
Connect a set voltage to it, measure the current through the.
So connect the voltage V.
Connect the voltage to it.
Measure the current I.
Yeah.
And then conclude R equals
E over I.
Good. Okay, and we built that off the relationship I equals V over R, or V equals IR, or whatever your favorite way of writing that is. Okay, I agree with everything Fred said. We started with just a resistor. I handed Fred a resistor. And he then thought to himself, I need to connect this to something and measure something. I can't just look at it and tell you the resistance. He connected it to a voltage supply, measured the current, and then did a ratio to figure that out. All right. Try to build off what Fred said now and think how we might measure the size of the capacitor, or the capacitance, C. Can someone get me started? Again, think how Fred thought through the previous one.
Cut the voltage source.
Connect the voltage source to it. Okay.
You could measure the voltage across the capacitor after like 5 minutes.
Okay, suppose I connect a 5-volt voltage source to it, and I measure the voltage across the capacitor after 5 minutes. In fact, after 1 minute, after a second, according to the fact that the voltage is around any loop added to 0, what will I read as the voltage across that capacitor? 5 volts. I will read that 5 volts no matter what the size of the capacitor is. So note that Fred had to measure something besides voltage. If Fred had measured voltage instead of current, if Fred goes and connects a 5-volt battery and he measures the voltage across the resistor, what voltage is Fred going to measure? 5 volts. Does that help him figure out the resistance? Not really. No, he needed to know that there was 5 volts, but measuring it here and then separately measuring it there didn't bring in any new information. So we connected a voltage source, we measured the voltage, and we've seen that that didn't quite work out. Can someone modify this approach a little bit to help? Brian?
Maybe had a resistor and got the change in
Ryan's got Ryan's way will work. It's long, okay? But it'll work. Ryan's saying, let's go with what we did last class a little bit, where let's connect the resistor, let's solve for an equation that determines the current through the resistor or the voltage across the capacitor as a function of time. Measure it as a function of time, maybe even plot both of them on Excel at the same time, try to do a curve fit, match them up. That'll work. It's not too bad. It'll take him about half an hour. And, well, actually, no, it'll probably take it's going to take him a half an hour to get all his equations straightened out, find the mistake, fix the mistake, get the minus sign right, go back, and then a half an hour to actually do it. So he's got a half an hour of work and a half an hour of thinking. This approach is going to be a half an hour of thinking and 5 minutes of work. So take your pick. Let's see if we can do something a little more direct. So you could do that. let's start. Well, maybe let's start. Let's solve this for C. What do I get if I solve that for C?
C equals,
DTI over UV.
so D, DI over DT, right?
That? Okay. That's the same thing as that, right? Whether you put the dt in the top. I like this way of thinking about it a little better, because I think I'll have more of a chance of understanding and thinking through dv dt as an idea than I will the dt dv. dv dt tells me how much does voltage change with time. As time goes by, the voltage changes. The reverse, dt dv, is saying how much does time change as the voltage changes. So, I mean, that's numerically it'll end up being the same thing. We don't really think of it that way. Time doesn't depend on the voltage. So voltage depends on the time. How this passage of time is occurring. It isn't being affected by some voltage somewhere. So I like writing this like that better. Okay, so to get capacitance, I need to know two things. I need to know an I and the dv dt. To measure resistance, I needed to get a voltage and a current. Now in Fred's case, Fred chose to apply the voltage and measure the current. So I can pick one of these two, apply one and measure the other. If I had a current source in the lab, which you do not have, you have to make your own. But if I had a current source, I could have applied a fixed current and measured the voltage across it. Okay, but I have to pick one of these two. One of them gets applied, and the other one gets measured. So I need to do something similar over here. In our lab, which of these two do you think would be easier to apply to the capacitor?
Fixed current.
So do we have a current source in the lab?
You can make it.
We can make one. Okay, so we could apply a fixed current and then measure dv dt. That will work. And I may have stated it too strong. I guess to me, it seemed 30 seconds ago, it was clear that applying this and measuring that was the easier way to go. However, several of you said that you'd rather take the effort to make a fixed current source, doing whatever that takes, and measure that. So it's maybe not as obvious as I was thinking.
So you're saying apply voltage over a certain period of time and then measure the current off of that?
Well, the question was which should I apply and which should I measure? Several of you thought, well, maybe applying a fixed current doesn't look so bad after all, and decided to go that way. Would that way work? Yes. And I guess as a teacher, I want to be very careful what is the science of this that has right and wrong answers versus what's an opinion on what's the easiest way to do something. This is an opinion, so this is not like right or wrong. Those of you who said, let's maybe apply this and measure that, fine. Okay. I think it might be easier to do the reverse. You'll see why maybe in a moment. But this is not one of those right or wrong things like most of the sources. I think it'll be easier to apply a changing voltage to something and measure the current. And we have ammeters, we can measure currents. So the question is, do we have any equipment that can apply a changing voltage without too much effort? Ryan's saying the WaveTech is in business for that purpose. So the WaveTech produces a changing voltage. The WaveTech can produce different shapes of changing voltage. You may notice on the front there are several different shapes it can produce. It can produce a square wave, it can produce a sine wave, it can also produce one other shape. Produce a triangle. Which of those three waves has the simplest form of dv dt? Is it the sine wave? Is it the square wave? Or the triangle? Which has the, in your opinion, the easiest way to manage the dv dt? Well, the slope of the sine wave keeps changing, right? So the slope of that sine, in fact, the slope of the sine is cosine. The derivative of sine is cosine. You've got that from calculus. So the slope of the sine wave curve is constantly changing. So it might be, we could use that, but I think it'll be a little bit harder. What's the slope of that square wave right there? Slope there?
Zero.
So okay, so the square wave doesn't work because the slope is always 0, except for a couple spots where it's not 0. When it isn't 0, it's really hard for us to manage. So here it's really big and negative, and here it's really big and positive, and it's really big and negative. And it might be tricky to figure out exactly what the slope is here and here and here and here, especially when the wave tech is doing its best to make that slope as steep as it can be. The triangle wave, though, as I think Isaac said a minute ago, seems to be the best contender for providing a steady dV/dt. The dV/dt here and here and here is all the same. Then it does switch. The dV/dt, which is, these are my slope symbols, is constant as it goes down, and then it switches, same value, but positive going up and then negative going down. So throughout this region right here, the dV/dt is a fixed number, constant slope. So maybe we could apply, instead of a set 5 volts to this capacitor, we could apply a triangle wave. I should apply a triangle wave and measure what?
How long it takes to get to 5 volts
Oh.
capacitor.
Okay, so I think, well, first there's no resistor here.
Okay.
So whatever this voltage is will be
Yeah.
applied to there.
Not a current source, a ammeter.
So Ryan's suggesting measuring the current.
Oh,
Do
when
you
it
agree?
equals
Do you think we're
0.
gonna need to measure the current? Am I going to need to measure the current?
Could you measure when it equals 0?
Because capacitance is I divided by dV/dt. Okay, one thing that might throw you off, and I think built into Junebel's question, is I can't unlike with resistor circuits, where nothing's changing with time. With a resistor-only circuit, I can measure the current with my meter, write down the number, take the meter out of the circuit, walk over to the cupboard, get a new battery, put it in the meter, come back, get a drink, measure the voltage, and then take the voltage divided by the current, get my resistance. That's fine, because nothing's changing with time. Okay, the fact that you measure one thing at one instant and the other thing at a different instant is perfectly acceptable. That's no longer true anymore. What we need to do is we need to measure that current at the same instant I measure dV/dt. I can't measure this current and then a minute later measure dV/dt. This current must correspond precisely to that particular dV/dt at that instant in time. I must measure the two simultaneously.
Fortunately, the dVt is pretty constant.
Correct. Correct. So, but what I can't do is before I even turn that on, measure the current. My current measurement has to correspond to dV/dt. So we should measure the current, I. Maybe use an ammeter to measure the current. And what is the shape of that current going to look like? So suppose I do apply this triangle wave. And let me make this picture a little bit bigger. So suppose I go into the lab and I apply a triangle wave that goes from plus 5 volts to negative 5 volts. And so on. And suppose the amount of time is 1 millisecond. Let's see if we can make a graph of the shape of the current versus time that will occur because of this. Now,
Should be a square wave, right?
yes. So let's graph the current versus time. And I put a couple points here. So Matt is suggesting it should be a square wave because this section right here, dV dt is not changing. It's the same value. dV dt here, which is the slope, the voltage versus time, is the same as there, which is the same as there. Is dV dt